Okay, today's video is a quick run through from this June 2022 paper. So because it was during COVID, they hadn't put the year on it because sometimes they cancelled the exams. So this is Pearson Edexcel International A-Level Physics, Unit 5. Okay, so Unit 5 covers thermodynamics, radiation, oscillations, and cosmology. But I'm only doing 2 questions at a special request for one of my students who found these 2 questions more challenging. Okay, so it covers circular motion, gravitational potential, and simple harmonic motion, which is from further mechanics, with some further mechanics in it. Okay, so if you find these kind of shorter videos useful, just leave a comment. Don't forget to like each video you watch. You find it helpful because the more likes and subscribers I get, the more videos of this nature I will be making. Okay, so I've gone straight into question 16, and although the first part is pretty straightforward, later on one of my students asked me to help explain this question beyond the mark scheme. Okay, so in question 16 it reads, the planets orbit the sun in approximately circular orbits. So we got circular motion. The orbital time of a planet, period of a planet, is related to the average distance r of the planet from the sun. Okay, show that t is related to r by the expression t squared is proportional to r cubed. Okay, so this is what we've got to show. And the way you do it is obviously the Newton's law of gravitation is the first equation you need to look at, and circular motion, F equals mr omega squared, is the second. You equate these two because the centripetal force is due to Newton's law of gravitation, and numerically that should be equal to mr omega squared, where omega is given by 2 pi over omega. Now you can see that the m cancels out, so you can simplify the equation and come up with omega squared equals gm over r cubed. Now we don't want omega in there, we want to put omega as 2 pi over t, so you're going to input omega equals 2 pi over t for omega squared, so that will make omega squared 4 pi squared over t squared. Yeah, so that's equal to gm over r cubed. And if you just make t squared the subject of the equation, yeah, so that's the same as the show that in the question. And r cubed is then on the left hand side, and everything else in between is a constant. 4 pi squared over gm is a constant. Therefore, it follows that t squared is proportional to r cubed, okay? Which is what we were asked to show. Hope that makes sense, and you'll have to look at the mark scheme to see the breakdown of the marks. The mark scheme is included in this run through. There it is. Okay, so there's more than one way of doing it, yeah, according to the exam. Alright, 16a part 2 then reads as follows. When the planets align as they orbit the sun, they are said to be in opposition. Okay, the diagram shows the Earth and Jupiter in alignment or in opposition. Okay, so there they are, in alignment. Okay. A website states that Earth and Jupiter are in opposition every 13 months. Okay? I prefer the term alignment, so that's what I'll be using because it tells you they're in a line. Deduce whether this statement is correct. So in other words, every 13 months, will they come back into alignment? So to do that, you've got to use t squared is proportional to r cubed. They've given you the distance of the Earth from the Sun and Jupiter to the Sun. Okay, so we know the values. And we know that the Earth takes 12 months to circle the Sun. So we want to find out how long it will take for Jupiter. So obviously we can use our mathematical knowledge to come up with the ratios, because remember, t squared over r cubed will give you a constant, as we just did in part A. So you can just do the ratios of the t squared to r cubes for each planet, as I've shown in the line, and you just want to work out the time period for Jupiter. According to the examiner, that comes to 142 months. I didn't check it due to not having a calculator and not having enough time. So the next alignment will be in a time t that we have to work out, where Jupiter completes part of its orbits, obviously. It's not going to take 142 months. And Earth completes its one orbit and then catches up with Jupiter, yeah? So the total time is greater than the orbit, the time period for the Earth. Obviously, it's going to be more than 12 months, okay? Because obviously, if it's only 12 months, Jupiter's moved from where it is now, so it's going to be 12 months plus t, okay? Since we know that omega is displacement over time, angular velocity is angular displacement over time, and we know omega is 2 pi over t, we can come up with a ratio of displacement against 2 pi must be equal to the time divided by the period. So for Jupiter, we can then make theta displacement, angular displacement, the subject, and to show that it's t over t, where t is 143 for Jupiter, multiplied by 2 pi. So if you can follow that, we're just making theta the subject of the formula, both for Jupiter and for Earth. Yeah? So the time will have to be t minus 12 over 12 times 2 pi for Earth, because we can take off the 12 months at the top. So basically t is the extra time on top of the 12 months. That it will be like 13 minus 12 over 12 is the displacement of the Earth after it does a full cycle. It's like you cancel out the 12 months. We just want to know the extra bit afterwards. So it's done 12 months plus t, okay? So we know that the angular displacement must be the same, so we can equate them by putting each of these right-hand side of these equations. So this one, equate it with this one, and that's how the examiner's done it. So there's for the Earth, equal to the value for Jupiter. And when you put all the t's on one side, first of all, you can cancel the pi's, because there's a pi on each side. Yeah, so pi's cancel out, which I've done here. So you can then put all the t's on one side. It comes to 3,408, and if you simplify it, it comes to 13.1 months. Therefore, the statement is correct. T is approximately 13 months to two significant figures. Now, there is an alternative method which the student who showed me was trying to do using angular velocity. So this is an alternative method. And what she did was she worked out the angular velocity for Jupiter, which came to this many radians in 1 month that it travels, and did it for the Earth. And obviously the Earth goes through a bigger angle each month. So that's for the value for Earth, again in per month. So you can see how she did it. And then she then tried to use the 13 months. And I told her you can't use the 13 months. You've got to prove the 13 months. So for the next alignment, as we know, Earth will travel a full orbit plus the extra theta to catch up with Jupiter's theta, okay? So because theta equals omega t, angular velocity times time. So theta for the Earth will be equal to the angular velocity of t, and we can take away 12 months worth of the Earth's angular velocity because it comes back to the starting point, and displacement means the net movement from your starting point, okay? It's kind of the vector quantity of distance for circular motion. And here you got the same equation for Jupiter, so they've got to be equal, as we said before. So WE times T minus 12 must be equal to WJT, okay? So we already know the values for W. So what we already know, I'll put in yellow, we know WJT, WJ, we know WE, and I think this is a neater method than the examiners. So the only thing we don't know is T. So we put all the T's together, yeah? So basically we're putting this value here, and this value here, and you're equating them. So this is, I think, a neater method than the examiners. So it gives you, this should be a minus, by the way, in here. I'm going to put it in red. This is a minus sign. It's kind of stuck to my T. Okay, so that should be a minus. Okay, so 0.52 for little t minus 2 pi, that's removing one full cycle of the Earth around the Sun, will be equal to 0.0439. Put the t's together and put the 2 pi on the other side, and you can see that I've actually come up with a new equation, which is this. And that should be generally true when you're trying to see if one faster planet, orbiting wise, can catch up with the slower planet in terms of angular velocity. This should give you the time at each time you do it. So it'll be 2 pi divided by the difference between the angular velocities, which is 0.48, which is basically what this is 0.48. And if you do that, you'll see that it takes 13.1 months for the Earth to catch up with Jupiter again. So this is a nice new equation for you to think about. And because my student brought it to me, it made me develop my own thinking on this subject. So I hope you found that useful in comparing my method with the examiners. Which one do you prefer? Leave a comment in the video, under the video, and tell me what you think of the two comparisons of the methods. I agree this is quite a difficult question compared to other questions in this paper, so it's why I'm going through it. Part B then says the distance of Jupiter from the Sun varies from 7.4 to 8.2 times 10 to the 11 meters. Okay, so the closest distance and the furthest distance. They want you to calculate the change in gravitational potential energy of Jupiter as it moves between those two, the closest distance and the furthest distance from the Sun. So the equation for potential is V equals minus Gm over R. So this is given to you. Obviously this is joules per kilogram. The unit should help you understand. So we have to put the mass of the Sun in this equation. Okay. And if you want to work out the change in gravitational potential energy, it's the potential times the mass of the object in the field. And the field is due to the Sun, because this is obviously joules per kilogram. If you multiply it by the mass of Jupiter, you will then get the potential energy difference. So first we have to work out the change in potential as being minus Gm, and then take away 1 over R when it's furthest away, yeah, as it moves from the closest. So this is also final, and this is initial. Furthest, 1 over furthest radius minus 1 over closest radius or distance is the correct way of putting it in the equation. And you'll notice that here we have a minus sign, and here we got a minus sign. So it's gonna become a plus there, and then this will become a minus. This one will become a minus when you simplify it. So I couldn't fit it all on one line, yeah, but here it is, minus G m of Sun divided by the final position, or the furthest position for Jupiter minus the closest position 1 over. So that's the 1 over r term. That's the difference between two potentials, and that gives you a value of 1.76 times 10 to the 7 joules per kilogram. We know the mass of Jupiter, so then you put it in here and you convert the change in potential to the change in gravitational potential energy, yeah, which is a bit like MGH, except MGH can only be used at the surface of a planet, okay? And this can be used at any position. So you multiply the potential by the mass of Jupiter, and you get the change in the potential when it moves from that place, from the closest distance to the furthest distance. It becomes positive because you're moving higher away from the sun. And remember, if you move away from somewhere, you're increasing the gravitational potential energy, and the minus signs actually do show that it's a positive change. You can then probably put it into two significant figures here. So you probably should simplify it to two significant figures from 3. Okay, there's the 11 marks. Okay, there's the examiner's answer that I used for part A, part 2, and here's part B. So that's question 16 completed. Okay, hope you found that useful. I'm going to go through one more question, which was question 17. And a man is about to dive into the sea from a high diving board. The board is horizontal before he walks to the end of the board. Okay, so it's not normally bent like that. When the man stands on the end of the board, it bends as shown due to his weight. So his weight is pulling him down and creating the bend in the board. By pushing on the board, the man displaces the end of the board a small distance, x downwards. Okay? The man and the board then oscillate because they're stuck together with approximate simple harmonic motion. So if it's simple harmonic motion, you automatically know that the acceleration must be in the negative direction compared to the displacement. Yes, if displacement is down, the acceleration when it starts oscillating will be upwards. Yeah? They want you to state the conditions for simple harmonic motion. Well, you can just see the mark scheme because this is a standard definition, and I was just short of time. I haven't handwritten it out, but we'll have a look at the mark scheme in a minute. That's a 2 marker. But basically this equation defines simple harmonic motion. A is directly proportional to x in the opposite direction. Okay? The man stands at the end of the board. The board is in equilibrium when the end of the board has a vertical displacement downwards of 18 centimeters. In other words, it's 18 centimeters or 0.18 meters downwards. Okay? The mass of the man is given as 75 kilograms, and it looks like they're ignoring the mass of the board. The board obeys Hooke's law as it deforms. So that we F equals kx. Yes? They want you to show that the stiffness of the board is about 4,000 newtons per meter. That's to one significant figure, just roughly. So you put F over x. Yes, you change the subject to make k the subject, which has the force is the weight of the man. Yes, so you put the mass in there, multiply it by 9.81, and divide it by the extension, which is 0.18. Okay, that gives you a value, calculated value of 4,088, and that's to 4 significant figures. If it was 2 significant figures, it would be 4,100, but it's to 1 significant figure, that is approximately 4,000 newtons per meter. I should really put the units in there, yeah, and that will get you the 2 marks. Okay, so now we know the stiffness. This is the definition of simple harmonic motion. I'll let you stop the video, and this is something that you just got to learn because it's going to repeat many times. Here's how they do the k value, yes, and they put it as 4,100 to 2 significant figures, which is approximately 4,000 newtons per meter to one significant figure. Okay? The next part of the equation is using t equals 2 pi root m over k, and then they want the frequency, which comes out to 1.2 hertz, by inversing the period. And you can see the calculation they've done here, which is exactly what I'm going to show you in the next question. So we've done what they've said. We put here, they can ignore the mass of the board, as I think I warned you before. We want to calculate the frequency of the oscillations. So first you've got to work out the period, put the numbers in, you get 1 mark, you get the period to 0.85 seconds, and then you inverse it to get the frequency to 1.18 hertz, 3 significant figures, but we only want accuracy to 2 significant figures for the sake of this question. So that's your 3 marks where the ticks are. This is the bit that I want to make sure you understand. The mark scheme is just has them down as bullet points, but my student didn't understand the reasoning of the mark scheme. You can either do it with forces or with accelerations. I think it's easier by looking at acceleration, because remember, A equals minus omega squared x, where the acceleration is inversely in the opposite direction to the displacement. So if the amplitude of the oscillation is large enough, yes, in other words, they're really bouncing that springboard, the diving board, up and down, the man will lose contact with the board at a point above the equilibrium position. Yeah, so if you push it down too much, it will make you jump off it when it goes up. Because for simple harmonic motion, so they want you to explain why, for simple harmonic motion, A equals minus omega squared x. So if the amplitude or the displacement downwards is large, then the man will accelerate upwards at a large rate. So the bigger the displacement, in proportion, the bigger the acceleration will be. Okay? So if the acceleration upwards is greater than gravity, acceleration due to gravity, yes, then what will happen? The man will lose contact with the board as the acceleration upwards is greater than g downwards. As the board oscillates back down, yes, the man will have a trajectory upwards still, because gravity hasn't slowed him down to 0. Okay? Now you can see I've actually done a calculation to prove it to you down below. So we know the frequency from the part before, so we can work out omega, first of all, using 2 pi f, comes to 7.54, and then we can use A equals minus omega squared x, yeah, to work out the acceleration, because you basically square omega, yeah, and the negative shows us the acceleration is upwards because the displacement was downwards. Multiply by that, you can see the acceleration is greater than g, so that's greater than g, and therefore the acceleration upwards is greater than g, therefore the man will lose contact with the diving board if they push it down 18 centimeters, okay? And there is the mark scheme. So I used this method with a proof mathematically using A equals minus omega squared x. So for my student, I hope you found this a clearer explanation than when you looked at the mark scheme on its own. You have to remember the mark scheme is written for the person marking the paper, not really written for the students. And you can always also look at it in terms of resultant forces, but I think my method is simpler, and I think with the calculation, it really does prove it to you that that's what happens. Okay, I prefer the A equals minus omega squared x. It makes more sense to me. Okay, well, that's the end of this 2-question run through for this 2022 exam. So I hope you found it useful. Please show your appreciation by liking each video you watch. And if you think it's useful to any other students who you might know doing this exam, please share it with them, and make sure you subscribe so you know when future videos are being uploaded. I recently uploaded 5 parts on the January 25, the most recent Unit 5 exam, so you should go and have a look at that as well. Unit 5 is on June the 4th, so that's in about 2 weeks' time. And anyone taking Unit 4 before that, end of May, next week is Unit 4. There's already quite a lot of Unit 4 exams, including January 25 and October 24 already uploaded on the channel. To see where the videos are, you want to go to the home page, yes, of my channel and look at playlists. So you want to look for playlists and look for the year of the exam and the unit of the exam. So it will show you the unit and the year. Okay, thanks for watching. Bye for now.